All right, so we're going to talk a little bit about photons and heat and how those two things are generated in chemical reactions. And we've talked some about this already. We're going to talk about it in terms of a couple other demonstrations. And so before we get there, we need to understand that burning, or the process of combustion, requires three different things to occur. And we all know that good chemical demonstrations, really fire is a big part of many of those. So if you think of demonstrations that you can remember, a lot of times you think of things that produce flames. It requires three different things. Number one, it requires an oxidizer. For us, almost always oxygen is going to be the oxidizer. It's possible that other chemical species could be used, but it's something that oxidizes the fuel, that oxidizes something that we're trying to burn, because essentially the combustion and burning is just another name for chemical oxidation or chemical reaction with oxygen. So when we talk about combustion or burning, that's what we're specifying. Secondly, it requires some heat, some energy to make the reaction go, to make the combustion start. And so it requires that we have that present, so that there's enough energy to make this process begin or make it start. Things don't generally just start on fire on their own. In fact, they don't start on fire on their own. It requires some source of heat or energy to make it go. So we need oxygen, we need an oxidizer, we need some energy, or we need some heat. And lastly, we need some fuel. Okay, something that will burn. We're going to talk a lot about the burning dollar demonstration, and the burning dollar demonstration requires isopropyl alcohol to make that go. That's the fuel. If you're thinking about the multicolor flames, it would be the methanol or the isopropanol that was dissolved the different salts. If you're thinking about the whoosh bottle, it would be the isopropyl alcohol. So anything where there's a fire, there has to be these three things: oxygen, heat, or energy to get the reaction going, and then some fuel that's going to burn. And you can see there's something called the combustion triangle or the fire triangle, where you need oxygen, you need heat, and you need fuel. And you can take any of those three things away, and when you take them away, the combustion or the burning will stop. So if, for instance, I would catch my lab jacket on fire in the lab, I could wrap myself up in a fire blanket, and that would remove the oxygen from the flame, from the combustion process, and so the flames would go out. If I was trying to put out a fire in a house, I might spray water on it or put water on it. One time we had a little campfire thing, not in the ground, but it's like a fire pit thing made of metal, and it dried the ground out underneath it so much that it caught our lawn on fire. So we had to get the hose out and spray it down. It wasn't that big of a fire, but I'm so cautious about fire that I was unhappy that it really stressed me out. But what we did when we sprayed the water on is we removed the heat from the combustion process, and when we did that, the fire went out. And so, if you remove the fuel, although that's a more difficult one, it will make the fire go out. That's the combustion of the fire triangle. So when we talk about the non-burning dollar, I don't know that you've necessarily seen that yet, but in an upcoming video, I'm going to show you the non-burning dollar. Is that you take a dollar bill, you dip it in this solution, the solution contains some fuel, you light it on fire, you get this great big bright fire, but the dollar bill remains intact after you've extinguished it. And what's cool about that is that it's cool that you burned something visibly, but that it doesn't turn to ashes. All right, it doesn't get burned, or at least if you do it right, it doesn't get burned. And so that's actually a pretty cool and pretty convincing experiment. I know that a lot of you were like, non-burning dollar is not big enough. It's, but it actually is really, really impressive to people in the room, especially if you use a larger dollar bill. So why doesn't that dollar bill burn? Well, first of all, generally what you'd use is a solution that's 50% water and 50% isopropyl alcohol. The isopropyl alcohol being the fuel, all right, and the 50% water being there to absorb heat. Why absorb heat? Because the heat from the fire is what would cause the dollar bill from the isopropyl alcohol burning would be what would cause the dollar bill to start burning. All right. And if you soak that in water, and really American dollars, this doesn't work with all dollar bills because most dollar bills from around the world are made of plastic. But in the United States, ours are made of, it's almost like a fabric. It's a paper, but it's very much like a fabric. And if you put that dollar bill in water, if you've ever had a dollar bill that gets wet, I mean, it retains that water. It's almost like a sponge. It's like a piece of fabric. It holds the water until it dries out. And that's the thing is when you dip that dollar bill in that 50% water, 50% isopropyl alcohol solution, it will absorb the water very, very quickly, and the isopropanol will burn, but the water will stay in the dollar bill. And then we know that already that water absorbs a lot of heat. And how do we know that? It's because we talked about the idea of heat in chemical reactions. And we know that, to increase the temperature of something, it requires some heat. Or if the temperature of something is increasing, then some heat must be added to the system. Likewise, if the temperature of something is decreasing, we must be removing heat or energy from that particular system. And we knew that we could determine this quantitatively using this specific heat expression, where heat equals mass times specific heat capacity times a change in temperature, where C is a specific heat capacity, tells us a little bit of something about how much energy is required to increase the temperature of that substance. Things with large heat capacities, it will take a lot of energy to increase the temperature of them. And we talked about water, and water having a specific heat capacity of 4.184 joules per gram degree Celsius. And that means it takes 4.184 joules of energy or heat to increase 1 gram of water by 1 degree, the temperature of 1 gram of water by 1 degree Celsius. And so if we think about specific heat capacity in terms of, a number of different substances, water tends to have a very large specific heat capacity, 4.184. And you can see that's double-ish, roughly double at least of any of the other materials that are on this list. And so water absorbs a lot of heat. So the water in that dollar bill is absorbing the heat from the flame as that isopropyl alcohol burns. So that's one way that, or one reason why the dollar bill doesn't burn. Number two, water can turn into a gas. And so some of that water is vaporized, turned from a liquid into a gas. We know that the enthalpy change for that reaction is very endothermic. It requires a lot of energy to vaporize water. 40.67 kilojoules per mole of water. And so we know it takes a lot of heat. So some of the water, the liquid water, is probably vaporized, but it required a lot of the energy from that fire to cause any of that to vaporize. So you have these two different processes that can occur, heating something up, or vaporization, or phase change. And both of those things require a lot of energy, and so those processes can absorb a lot of the energy that's produced by that flame. Now, some of you were planning to talk about this idea or do this demonstration where you hold bubbles, and the bubbles are containing methane, natural gas, that can then be combusted. And you can see here, Katie and Tim, they're students from years ago that they were part of a demonstration show that the students put on. And what they would do first is they would bubble some methane gas, some natural gas, through some soapy water. It would form bubbles, and now inside those bubbles is not air but methane, which is very flammable. then they would take their hands, but they would make sure, and you can notice Tim's hands are holding those bubbles, and Katie has lit them on fire on the right. And you can see this great big fireball that goes up. Now the thing that makes Tim not get burned to a crisp, makes his hands not burn, is that he made his hands very wet before he picked up the bubbles. And so the water will, number one, absorb some of the heat from the fire. Its temperature will increase a little bit, but not a lot. And secondly, some of that water in his hands will vaporize, and that requires a lot of the energy. So, we have these processes that are absorbing a lot of the heat or the energy that's evolved in the combustion process. And that's keeping his hands from burning, which is really cool and it's really spectacular. But in reality, this is just the non-burning dollar demonstration being done in your hand. So, the heat from the flame. So one of the other things that you might have noticed is that what's happening in this particular demonstration, or if you notice the flame in Tim's hands, it turns his bright yellow. That can be from a couple of different reasons. Number one, it can be that that flame is what we call a diffuse flame, meaning that it doesn't have a lot of oxygen around, or the oxygen in the correct proportions, or in a proportion where oxygen maybe isn't as prevalent. And so, therefore, the flame will have a yellowish color or be a lower temperature. If you had more oxygen, it would probably burn hotter, but the oxygen's getting into that flame by diffusing from the atmosphere into that fire, which can be kind of a slow process. If you premix oxygen, so if we'd put oxygen gas in with that methane gas, that flame would have burned a whole lot hotter, and it probably would have burned him at that point. So why does that flame turn yellow? Well, that flame turned yellow because it was diffuse. In the non-burning dollar, it's generally because we've added something to it. So, the flame colors that we're going to talk about now really don't have anything to do with diffuse versus lean flame. It has to do with the fact that when I do the non-burning dollar demonstration, I actually put some sodium chloride into the solution that we dip the dollar bill in. And when you dip that dollar bill in that solution, it picks up some of the sodium, and then the heat from the flame actually will cause the energy of the valence electrons in sodium to move around. It'll cause those electrons to move. And so when we're talking about sodium, remember the electron configuration for sodium is 1s2, 2s2, 2p6, 3s1, where that 1 3s electron is the valence electron. All right, so that's the one that we're going to be talking about here. That highest energy electron is the one that we're going to cause to move around, or most likely going to cause to move around. And the energy from that fire, from that flame, makes that energy move to a different orbital. It's going to move to a higher energy orbital. So that electron gains energy. It's going to move to a place where it will have more energy. More energy it's more likely that something with more energy would exist. And what I mean is it's going to move to the 3p orbital that has higher energy. So you can see here in this diagram, it shows we can make that electron actually jump from the 3s orbital to the 3p orbital. We can make it jump from the 3s orbital to the 4p orbital, or we can make it jump from the 3s orbital to the 5p orbital. We call this movement of an electron back and forth between energy levels, we call those transitions. So there are 3 different transitions that valence electron in sodium can undergo. The one that we are talking about, the energy that we are giving to it with this flame, is the transition between the 3s and the 3p orbital. We make it move to that 3p orbital, and it stays there for just a very short period of time. And when I mean short, I mean like nanoseconds or picoseconds or femtoseconds. I mean, we're talking like really, really short periods of time, then it stays there. But it goes there because we've given it more energy. That fire has given that electron more energy, and so it ends up in that 3p orbital. And so now it's got a lot of energy in the 3p orbital, but it wants to go back home to the 3s because it's a lower energy state. And when it does, when it goes back down to the 3s, All right, when it relaxes, it's called relaxation. Going to a higher energy level, for like the 3s to the 3p, would be called excitation. And then when we go from the 3p back down to the 3s, we'd call that relaxation. And so the electron has that extra energy. It comes back down to the 3s, but in the 3s orbital, it can't keep that energy. All right, 3s orbital is a lower energy state. And so it's got to give that energy away, and it gives it away in the form of a photon. All right, and that photon, all right, the energy of that photon is corresponds to the energy difference between the 3p and the 3s orbital. And it just so happens in sodium that the difference in energy between the 3p and the 3s orbital corresponds to a photon of 590 nanometers of light. All right, and remember that energy of a photon is proportional to 1 over the wavelength of light. So, the energy of a photon, this photon would be 590 nanometers, which is a yellowish-orange color. And that's what we see whenever we have sodium in a combustion process, is that we see this bright yellow or bright orangish color. It's because of that transition of that electron between the 3s and the 3p orbital. And you can see here is the dollar bill that I had burned, or that I did using the non-burning dollar demonstration. And when those flames extinguish, all right, the flames go out, and you're just left with a wet dollar bill. Doesn't even feel warm. It feels cool. All right. So flames produced with alcohol as a fuel generally tend to be kind of blue or clear, invisible in color. Those Indy race cars, if you've ever seen them, the ones that have the wheels sticking out the side, they're sort of open wheel cars. And they look almost like they have like a wing or a baffle thing on the back to keep them on the ground, so they don't fly away. Those generally are fueled with alcohol, and a lot of times the flames, when they catch on fire, you can't see the flames. And it's pretty much the same with alcohol. It will burn like a bluish color maybe, but very, very light. You can barely see it. Here we can see it very well because there's sodium added, and that transition of that valence electron to sodium is the reason why we can see that flame so brightly. And so that's what's happening in the non-burning dollar. Now, we've seen this as well, the same phenomenon with the multicolor flame, where you can take a solvent, a fuel that burns, we can spray that into a flame, and it turns a brilliant color. Here you're seeing boric acid being sprayed into the flame. It gives us a green color. And on the right, you're seeing potassium chloride, because potassium has a purplish, pinkish color when you see the transitions of its valence electrons. And so we can see these different things. So those are a bunch of different demos sort of like stacked all together in one. But just giving you some idea why. First of all, why is it that the non-burning dollar experiment works? Why doesn't the dollar bill burn? And if you don't get that ratio between water and alcohol right, your dollar bill will burn. You have to have enough water present to absorb that heat. But also, it tells us why this lecture has told us why the non-burning dollar doesn't burn, but it also tells us why it is that flames have particular colors. They can be either lean or diffuse, or they can have other substances that are inside of that flame or in the material or mixed with the fuel, that the valence electrons move up and down between energy levels. So that's it for this lecture. We will pick up, and there will be a number of different demonstrations for you to see. The whoosh bottle, probably the non-burning dollar. I'll do that again so that you can see those. And those will show up probably sometime on Friday.